Good afternoon. I'm Frank Ling, and this is the Berkeley Rock Science Show.
That's right. It's a weekly look at the world of science, technology, and their effects on our daily lives. I'm Charles Lee.
Coming up on today's show, animal hybrids, mating gifts, and throwing it up.
In addition, we'll be joined by Professor John Stachel, who will talk about Einstein's miraculous year.
Also, we'll find out what are the largest telescopes.
So stay tuned for all this, plus the Grokatron 5000 and the world-famous question of the week, coming right up here on the Berkeley Grok Science Show. You are listening to the Berkeley Grok Science Show. Well, joining us in just a few minutes is Professor John Stachel, who will discuss Einstein's miraculous year. So stay tuned. Welcome back to the Berkeley Grok Science Show. Well, after 1905, physics would never be the same again. In those 12 months, Einstein shattered many cherished scientific beliefs with 5 extraordinary papers that would establish him as the world's leading physicist. This is the year that we celebrate Einstein's miraculous achievements, and joining us today to discuss Einstein's miraculous year is Professor John Stachel. Professor Stachel is Professor of Physics Emeritus at Boston University, where he directs the Center for Einstein Studies. He is the editor of the book Einstein's Miraculous Year, 5 Papers That Changed the Face of Physics, which is just in a new edition. Professor Stachel, thank you very much for joining us today on Berkeley Groks.
Happy to be here.
Well, certainly a pleasure to have you on the program, and you've certainly edited, I think, a very fascinating book, Einstein's Miraculous Year. But I guess I'm curious, for those maybe who are a little outside of physics or even academia, if you could give a sense of just how miraculous, how amazing his achievement was during this year.
Well, maybe I'll disappoint you, but I don't think it was the most miraculous year in Einstein's life. Actually, I think his work on the general theory of relativity, culminating at the end of 1915, was the most miraculous accomplishment. Einstein's miraculous year in 1905 was a year in which he suddenly appeared from nowhere and made a place for himself on the face of theoretical physics. But this made him well known in the physics community within the next few years. But it wasn't until his work on the general theory of relativity, culminating in the final formulation of the theory at the end of 1915, and then the confirmation of his prediction of the bending of light, of starlight that passed near the sun's limbs, that Einstein became a public figure and known outside of the physics community. That didn't take place until 1919.
I see. But many of his papers that he did write during those years eventually led to his Nobel Prize and then another Nobel Prize for another person. Yes,
that's true. His accomplishments could be divided into 3 main groups. First of all, he continued classical physics. It's a myth that he was entirely a revolutionary figure. One of his greatest accomplishments was to continue to complete the development of classical physics. The second group of papers was, again, an attempt to resolve the problems that had arisen in trying to combine classical physics, which was basically a mechanistic view of the universe, with classical electrodynamics, Maxwell's theory. And the attempts to do this on the basis of the Newtonian views of space and time proved impossible. And Einstein, therefore, had to develop a new conception of time primarily, and then from that, new views about space. And this was his work on the special theory of relativity, which resolved the apparent contradictions between mechanics and electrodynamics.
I see.
But the only work of his in 1905 that he himself described as very revolutionary was his work on the quantum theory. In this paper, he went beyond Maxwell's electromagnetic theory of light, that light is a classical wave, to the viewpoint that there's a particulate or particle aspect to light. And he called it at that time the light quantum. And what he showed was rather limited at that time. He showed that in a certain range of frequencies, a high-frequency limit, light behaved as if it were composed of a series of statistically independent particles. But he was very cautious because he realized that light could not be simply a classical gas of particles. And indeed, it was only 20 years later that the quantum mechanical theory of gas was developed, which could treat the photon as not a classical gas of particles, but quantum mechanical gas of particles. But this work on showing that one had to go beyond Maxwell's theory of light and electromagnetism in general to a quantum theory of light was the beginning of the true quantum revolution, which, as of 1905, Einstein already recognized as something quite revolutionary. And he was the first person to say that not only classical electromagnetic theory, but classical mechanics would have to be modified to take into account of these new quantum phenomena, which he pointed the finger at as the truly revolutionary development of 1905.
Wow. Basically, as you mentioned, sort of paved the way for the field of quantum physics, really.
Exactly. Max Planck had introduced the idea of the quantum of action in 1900, but Planck was extremely conservative and tried his best to show that the quantum of action could be fitted into classical physics. As I said, Einstein was the first one to clearly say no. Not only classical mechanics, but classical electromagnetic theory will have to be modified in view of the existence of the quantum of action. And within a few years, he showed that not only light, but the vibrations of a solid body would have to be quantized, have to be treated as a quantum effect in order to explain the behavior of solid bodies at low temperatures. So that it was actually this work, an Einstein's application of the quantum theory to solid bodies, the quantum theory of a vibrating solid, that made Einstein's name most famous among physicists at that time, because this had immediate consequences for the kind of research that was going on to explain the specific heat of solids at low temperature, which had previously defied explanation. And actually, that is his work on that in that field that brought Einstein to the attention of the Berlin group of physicists, who ultimately invited him to join them in Berlin as a member of the Academy of Sciences. This took place at the end of 1913, beginning of 1914, and that's the reason why he moved to Berlin. So it was not the other papers that we've been talking about, but his work on quantum theory of solids, which was done in 1907, that really brought him to the center of attention in the physics community.
Right. Well, I guess as you mentioned, most people don't realize that was what he won the Nobel Prize for.
Well, that's a curious story indeed. Yeah. By 1921, when he'd been considered for the Nobel Prize several times, but by 1921, when he finally was awarded the prize, there was a member of the Nobel Prize Committee, a Swedish psychophysiologist, who applied some complicated mathematics to the study of the behavior of light in the human eye. And this man was on the Nobel Prize Committee, and he thought he had discovered a flaw in Einstein's theory of general relativity. And for that reason, he refused to allow the committee to give Einstein the Nobel Prize for work in relativity. So they decided, well, to give him a prize for his work on the photoelectric effect, which was one of the consequences that Einstein drew from his work in 1905 on the quantum theory of light. It was not the central point of that theory. It's often called the photoelectric effect paper. That's, again, a misconception. Einstein's papers, particularly his early papers, typically took the following form. There were three parts. First, he would propose some paradox or some puzzle in existing physical theory. Then he would propose a solution to that puzzle, and then he would look for the experimental consequences that would enable one to test whether that solution was valid or not. And in the quantum paper, the photoelectric effect only occurs in the third part, where he's looking for some physical consequences of his light quantum hypothesis. So it's far from being the photoelectric effect paper. That was just one of the tests he suggested to see whether his light quantum hypothesis had any validity.
Right. Well, isn't that normally the case, I guess, with Nobel Prizes? Oftentimes, they don't always recognize the particular achievement which the scientist necessarily.
That's absolutely true. If you drew up a list of all the Nobel Prize winners and asked people, first of all, have you heard of these Nobel Prize winners? Most physicists wouldn't even have heard of most of the Nobel Prize winners of the past. And if you ask what were the prize given for, you often get the wrong answer from the physics community. But this is often true in human life, isn't it?
Sure.
One gets rewarded for the wrong things and punished for the right things. That we do.
C'est la vie, as you say.
Yes.
Well, I mean, I guess there's no real way to rank it, but would you say that perhaps those two papers that he wrote on special relativity rank a little higher or perhaps more influential than the other papers?
I would say they were comparable. The quantum paper, after all, started the quantum revolution, which we're still experiencing the consequences of. The papers on special relativity certainly revolutionized the way that other questions in physics were approached. These were example of what he called the theory of principle. They didn't tell you anything concrete about the nature of the world, but they told you if you're going to describe how the world is built, you must take into account these principles. I often compare them to traffic rules. The traffic rules don't tell you where to drive, but they do tell you if you don't want to get arrested, you better obey the traffic rules. So the principle of relativity and the light principle, the two basic principles of the special theory of relativity paper, are just that, principles. They tell you if you're going to construct a theory of matter or radiation, you'd better observe these principles or you won't get an acceptable theory. But they don't themselves constitute constructive theory. So all the basic work that was done in constructive physics from 1905 on had to be based on the special theory of relativity. But as early as 1907, Einstein realized that if he were going to include gravitation within this constructive theory of physics he was looking for, they would have to pass beyond special relativity. And there, again, he was quite alone. All other physicists were still trying to construct a special relativistic theory of gravitation. They'd accepted his own work at a time when he saw he had to go beyond it to proceed. And his great achievement, as I said, in 1915, was to show how one could construct a generalized or general allgemeine in German, which really might be better translated, a universal theory of relativity. And this was his theory of gravitation and inertia. And again, we're still today trying to understand how to reconcile his theory of gravitation and inertia with his ideas about quantum theory, which have developed into quantum mechanics. Today we have basically two separate branches of physics, each of which lays claim to fundamental significance. Quantum theory, in particular quantum theory of fields, the special relativistic version of quantum theory, and general relativity, the best theory of gravitation and inertia that we have today. And these two theories are basically irreconcilable at the foundational level, yet they both claim to describe, in certain regions, the same phenomena. And therefore one must look for a greater and more all-encompassing theory which could include both. and that's the search for what we call a theory of quantum gravity.
Right.
Now, quantum gravity is like X in algebra. It's just a name for the unknown. We don't have such a theory.
Right.
It's the search for some way to construct an all-encompassing theory which would, on the one hand, contain general relativity as one limit and quantum field theory, the best theory we have of quantum phenomena, on the other. And that's, I think, the great challenge which we're facing in theoretical physics today. And I've been devoting a lot of thought and giving some talks on this problem myself.
Right, indeed. And indeed, Einstein spent many of the last years of his life actually trying to work out a grand unified theory.
Well, this is a little different than unified field theory.
Yeah.
The unified field theory, Einstein's hope was modeling himself on Maxwell's work in the 19th century. Maxwell had achieved the great success he did by taking electricity, magnetism, and optics, which were originally three separate fields, and showing all of these could be unified and explained in terms of one classical electromagnetic theory. We now call it the classical theory. Of course, at that time there was no quantum theory to contrast it with, so it was just the theory of electromagnetism, Maxwell's theory. Einstein said, well, now, after 1915, he said, now I've explained gravitation and inertia. I've united those two. How about electromagnetism? Why should we have electromagnetism separated from gravitation and inertia? Let's look for a theory which combines the two. That was the search for unified field theory. Einstein also felt, well, if you succeeded in building such a theory, constructing such a unified field theory, and could find non-singular solutions to that theory, solutions which did not have places where the fields blew up, maybe those solutions would themselves be quantized. In other words, they would themselves give you the explanation for the quantum phenomena, the discreteness that you find in quantum phenomena. That hope never was realized, and for a long time, unified field theories fell out of fashion. Today, they're back into fashion, but not in Einstein's sense. That we believe now that if you're going to find a unified field theory, first you find the classical theory and then you quantize it. And so that search goes on. But there's a different question from the question of can one take existing general theory of relativity, the best theory of gravitation and inertia that we have, and quantize that and make that somehow compatible with the quantum ideas.
I see.
And some people say, well, if you're going to do that, you're going to have to take everything into account. That's essentially the path of string theory, that a quantum gravity theory will only emerge from a theory of everything. But myself, coming from the general relativity tradition, we have a much more modest aim. We say, let's try to find a form of quantum theory which is compatible with the basic principle of general relativity, and then apply that to Einstein's theory of general relativity and get just a quantum theory of gravity without looking for anything more grand or unified than that. Only the future will tell which path is the right one.
Certainly, string theory has got a little bit of press, but it seems to be as pie in the sky just because you can't really experimentally verify a lot of their
and indeed, they even
predictions.
they haven't fulfilled their theoretical hopes. When I make theoretical criticisms of string theory, people often say to me, well, but, you know, what you say might be valid, but if the theory works, what are you going to do about it?
Right.
Yes, I say that's true. Nothing succeeds like success. On the other hand, nothing fails like failure. And in 20, 30 years of work on string theory, they haven't really come up with the kind of explanation they originally were looking for, let alone any experimental consequences of their approach. So the better people in string theory admit that the program really has not succeeded as yet. So as I said, if nothing succeeds like success, we have to agree that nothing fails like failure.
Indeed.
So I'm not saying string theory won't ultimately succeed, but so far there is no hint that it is any further along the path to success, let's say, than loop quantum gravity, the approach to quantization of general relativity, which is favored by most people working from the general relativity tradition.
I see. We do have a few more papers that Einstein wrote at one point, one describing, I guess, Brownian motion, which led to another Nobel Prize.
Yes. This was part of the first strand of his thought. Take classical physics and develop it as far as you can and see what problems within classical physics remain. Now, one of the main aims of classical physics, as developed in the course of the 19th century, was to explain the laws of thermodynamics, the behavior of bodies when they not only experience mechanical changes, but thermal changes, when heat is added or subtracted to them at the same time they're doing work or having work done upon them. And the hope was that one could explain the laws of thermodynamics, which are, again, principal laws, like Einstein's principal theory of relativity. In fact, that was his model for the special theory of relativity. Thermodynamics is just based on two principles, the conservation of energy and the fact that heat always flows from the hotter to the colder body, which is basically the second law of thermodynamics. Well, the hope was to explain all these in terms of mechanical terms. Think of matter as constructed of a lot of molecules or particles, whatever you call them, atoms, just molecules for short, let's say, moving around very rapidly and interacting with each other. And can you explain the laws of thermodynamics on the basis of that model? Well, people like Maxwell and Boltzmann and Clausius said, yes, you can. And they went a long way to try to show that. There was another school of physicists, and particularly physical chemists, at the end of the 19th, beginning of the 20th century, said, no, we have to take phenomena as they are, and conservation of energy is the most important law. The laws of thermodynamics should be explained purely in terms of energetic concepts, and they should be exact laws. If the people who were trying to explain the laws of thermodynamics on the basis of kinetic theory of matter were correct, the thermodynamic laws should only be statistical laws. They should only be true on the average. Just like if you flip a coin 1,000 times, heads will come up half the time and tails will come up half the time on the average. But you're going to get fluctuations from that.
Right.
You may get a run of 10 heads before you get a tail. You may get a run of 3 tails before you get a head.
Right.
That's to be expected on the basis of statistical fluctuations. Well, on the basis of kinetic theory of matter, that matter is composed of molecules moving around rapidly, and pressure and temperature and so on are just average effects of these motions, there should be fluctuations around these average values. And Einstein's great achievement in the Brownian motion paper was to show that these fluctuations not only should exist, they had actually been observed. That Brownian motion could be explained in terms of fluctuations around about the thermodynamic averages. So when you look in a microscope and see the little particles moving around on the Brownian motion, you're actually observing violations of the laws of thermodynamics. And Einstein was the first one to realize that. And this more or less killed the anti-atomist trend. After that, it was very hard to say, no, the laws of thermodynamics are exactly correct. Once you've actually seen the fluctuations, which the opposed kinetic molecular theory had predicted.
Right. It's really amazing. And I guess one of the questions is, how was physics really changed from all these papers? You sort of allude to it, but maybe sort of as a grand, from the classical views then to the more modern views.
Well, two things. First of all, he solidly established the kinetic molecular theory, so that the challenges to that more or less had to end after Einstein's theoretical work and the work of Jean Perrin, to whom you alluded, who won the Nobel Prize for his experimental verification of Einstein's predictions. Then his work on the special theory of relativity led him into the general theory of relativity, which I would say was the most fundamental change that Einstein brought about in our view of the world. And he himself regarded his work on the general theory of relativity as his greatest contribution, because all physics up to then, and indeed all physics after then, insofar as it's based on quantum theory, was based on the idea of fixed and given space-time structures. Now, he showed you how to modify the Newtonian concept of space and time, but in special relativity, you just replaced the Newtonian concept of space and time by another fixed and given concept of space and time, what we call Minkowski's space-time for short. But in the general theory of relativity, he showed something much more revolutionary, that the space-time structures themselves are not fixed and given, they are dynamical fields themselves. So space and time is no longer the stage on which the drama of matter and radiation unfolds. It is part of the drama. And this was so revolutionary that to this day, I think we're still trying to assimilate the effects of this revolution. So that's the second revolution, more general relativity than special relativity, but special relativity was the prologue to that. And then the quantum revolution, to which we alluded earlier, which he showed that classical physics had to be totally revamped and rebuilt on some totally new foundations. And as I said, to this day, we're still trying to bring these two revolutions, the general relativistic revolution and the quantum revolution, into some sort of accord with each other, because so far they've gone their separate ways, and the attempts to bring them together into one grand quantum theory of gravity have not been successful. I would say, as I said before, I think that's the challenge of this century, and maybe of this millennia, to bring this about.
So I think this actually brings up an interesting question. Do you think that there will be another person like Einstein, or a year like Einstein had in 1905?
It's probably harder today because not only did there were revolutions within physics, but there was a revolution in the way physics was done, which took place at the beginning of the 20th and into the 20th century. Namely, physics made the transition from handicraft to large-scale industry. At the time Einstein worked, the typical laboratory was one professor with a few assistants and one theoretician working alone or with one or two collaborators. But today, of course, we've made the transition to what I could call factory physics, these huge machines which we have, which employ hundreds of people. Today you'll see a paper signed by 20 or 30 people, most of whom are graduate students who've been dragooned into working on their professor's project and may have little or no idea what's actually going on in the project. I regard this as a very sad development, that at least when a student does a PhD project, that person should realize, well, maybe I'm only going to add a little brick to the wall of knowledge, but I better understand how that brick fits into the wall and what the wall is composed of. And I'm afraid many physics students are not getting that training today. They're being put out into the world with a PhD without any real understanding, deeper understanding of the work that they themselves have participated in. So I'm afraid this transition from handicraft to large-scale industry makes it much more difficult for independent-minded people like Einstein to succeed. On the other hand, independent-minded people, really independent-minded people, always find a way around the rules, and they find a way to succeed.
Indeed.
So we can hope that other Einsteins, male or female, I think more and more women are going into physics. We might hope the next Einstein might be a Miss Einstein.
Yes, indeed. Curious, just to sort of try and wrap up, obviously you're a physicist, but I'm curious, how did you actually become interested in Einstein in particular and actually directing the Center for Einstein Studies?
I became interested in Einstein in the 1950s. I both was interested in his scientific work. As a young high school student, I started to read about theoretical physics and came across the name of Einstein, obviously, and started to think about his ideas. But I also respected him greatly as a political and social figure at that time. This was the time of McCarthyism in America. Not Gene McCarthy, but the Senator McCarthy from Wisconsin, who was trying to introduce witch hunting in the country. And Einstein was one of the few intellectuals who stood with moral principles, with a backbone, I would say, and said, no, you must refuse to cooperate with inquisitions, witch hunts, and not on the basis of the Fifth Amendment, but on the basis of the First Amendment, that Congress or any other body has no right to pry into the personal political opinions of any individual. And if you have to go to jail for that, Einstein said, so be it. I'm willing to go to jail for that purpose. And that was a great inspiration to people like myself on the left who were so upset to see how many intellectuals were caving into the pressures on them at that time. So I came to revere Einstein both as a scientist and as a political and social figure. And I'm afraid today we have need, again, of moral examples like Einstein's when we see how many intellectuals are caving into the pressures at a time, again, when America is being led on a path of militarism and a path of violations of our civil liberties. The kind of things, incidentally, which Einstein warned about as early as 1947. Right after the end of the Second World War, beginning of the Cold War, Einstein wrote an article on American militarism, which he foresaw the possibility that we would get into a stage where we would have preventive wars, violations of civil liberties, all of this being tolerated by people because it was done in the name of fighting some sort of vague threat. That time was Bolshevism, communism. Today it's international terrorism. Well, everybody's against terrorism, but some of us are against state terrorism, not only terrorism by individuals, but terrorism by the state. And to fight terrorism by another form of state terrorism is just creating not only an error, but more terror.
Indeed.
And I think Einstein is a great example for us of moral courage in calling the shots as we see them and trying to fight for the kind of America we want to see.
Indeed, indeed. Well, he certainly was a remarkable man in many areas, but it does look like we're slightly out of time. And Professor Stachel, I do want to thank you very much for joining us today on Berkeley Groks and talking about Einstein's Miraculous Year.
Thank you very much. I'm very happy to be here and certainly hope many people will not only revere Einstein, but read him and think about his ideas. As somebody said in the 18th century about another German poet, who wouldn't praise a Klopstock? We'd rather be praised less and read more.
Hear, 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 hear. And you were just listening to Professor John Stachel discussing Einstein's Miraculous Year. You are listening to the Berkeley Groks Science Show.